Recording. So what we're going to be looking at today is parent functions and transformations. So basically, here are some of the most common parent functions we'll kind of see in this class. So we'll have like a constant function is just like a straight line. If you have f of x equals a number, that's basically like y equals a number. Remember, y equals a number is a horizontal line. We'll look at our standard equation of a line. F of x equals x is just your standard line. If you've never graphed an absolute value, it just makes this V shape. You should have seen quadratics before. That makes the parabola, or your standard U shape, is just x squared by itself. This kind of bent looking paperclip is our x cubed function. This is the square root function. It just kind of starts at 0 and kind of makes like almost half a sideways parabola. But basically what a parent function is, this is what your function looks like before you add any extra things to your equation. Like you just have the square root of x, nothing more. You just have x squared, nothing more. So these are kind of like the OG functions. This is what they look like originally. And we'll look more at these functions later, kind of like seeing how we graph them if you're not familiar with some of them. Most of these you're probably pretty familiar with, but I guess for me, absolute values, cubic, and square roots might not be a function you're super familiar with seeing, but the other three, hopefully, I mean, lines we've done this year, and hopefully you've at least seen quadratics before, like the parabolas. Oops. So kind of the idea is we will start with these original functions and then we're going to add rules. So one nice thing about these rules is if you know your original function, you can just move the points based on what the rules are telling you. So that's really what we're going to be doing. We're like when we have a question, we're first going to ask ourselves, well, what's the parent function? And then we'll start with our parent function and move it based on the rules to get our new function. So when you see questions today, the first thing you really want to ask yourself is, one, what parent function do you have? And then two, what are my transformations they're asking me to do to this function? So we talked about these yesterday, but I kind of want to just go through these one more time, make sure they're clear. If you have a number outside your parentheses, and we'll kind of see some examples what I mean by that, but if it's outside away from your variable, if it's plus, you move your function up. If it's minus on the outside of your variable, it goes down. So this k value in this formula tells you if you move it up or down. If you have a number inside the parentheses or inside with your variable, we'll see, because sometimes different functions, like if it's a square root function, it's inside the square root. If it's an absolute value, it's inside the absolute value. But if it's inside with your variable, it's kind of backwards of what you would expect, but plus on the inside means you go left. Minus on the inside means you go right. If you have a negative in the very front of your function, so for example, if you had like negative x squared, like a negative right in front of your variable, that means you're going to reflect over the x-axis. Honestly, I will double check, but you're probably not going to see this rule today. But if you have a negative inside, like parentheses with your variable, you would reflect over the y-axis. But I don't believe you will see this one in any of the delta math questions today. I didn't see it in any of the ones I tried, but I guess in theory it could be asked. So I'll let you know if I see one. If you have, it's so similar if you have a negative in front, but if you have a number multiplying in front and it's greater than 1, it's a vertical stretch. So like, for example, if you had a 2 in front of your function, you're going to multiply all your y values by 2. That's what I mean by a vertical stretch. Like all your y values are going to grow by the factor that's in front. If you have a fraction, so like a number between 0 and 1, you're actually going to have a vertical compression. We're going to see that our y values shrink. And honestly, this one here that I'm starting, you're not going to see today in delta math. So if you kind of want to ignore those rules, or like, I'm just going to tell you what it is just in case you ever are exposed to it. But in this class, you won't really have to know these two rules I'm starting. Like, I won't give you any questions on a quiz where you're doing those rules, unless I made it like a bonus question, maybe. But I would never ask it for like a legitimate question on a quiz. So just FYI. But if you have a number inside your parentheses, like a factor, if it's greater than 1, it's kind of opposite of what you would expect. It actually compresses when it's bigger than 1. It's kind of like the subtraction and addition. It's kind of backwards of what you would expect, but it compresses. Sorry, I should have put horizontal compression, but it's a horizontal compression, or compresses horizontally, so it shrinks inwards, left and right. If you have a fraction factor on the inside of the parentheses, it's actually I'll just write it in the same order here, but it would be a stretch horizontally, or a horizontal stretch. But to be completely honest with you, these rules that I'm starring, you will not need to know, or you will not see in any of the problems, I believe. I will double check and let you know if I see any, but at least in terms like when we have our next quiz over the second part of chapter 2, I will not ask you any questions that involve those rules unless it's for extra credit. What we're going to do next is we're going to look at our parent functions. I'm going to kind of try and familiarize ourselves with these, and then we're going to talk about what the domain and range of each function would be. So our first function, y equals c, actually give me one. All right, but looking at our first function, y equals c, this one's kind of a weird, whatever your c value is, so for say, for example, our c was any line, it's just going to be, oh, that's really sloppy. It's just going to be a horizontal line. So this problem doesn't really have always the same function. It depends on what your c value is, but it's just going to be a horizontal line. Some things to note, your domain, here, I'm going to type this because I need to make sure I'm being kind of neat, because I'm going to squeeze some stuff in here today, but our domain would be, I'll write it, in our range. So let me move this. Where'd it go? Oh, I shrunk it so you can't see it. All right, I'm just gonna write it. Okay, so our domain, I'll write it below. Our domain, since it goes left and right forever, it would just be negative infinity to infinity for like all of these functions, no matter what your c is. One symbol I kind of want to emphasize is that negative infinity to infinity, you can also write this symbol all real numbers. Like I'll write it up here a little bit bigger. But if you, a lot of these functions are going to have this, but if you have positive infinity, or sorry, negative infinity to positive infinity, another way you can write that is all real number. Basically, you draw like 2 parallel lines vertically, and then from the second one, you kind of draw an R. That just means all real numbers, basically. It has every number. So I might use that symbol for some of these just because it's a little shorter to write. Our range, well, it would just be your c value. So whatever your c value, that's the only y value you'll have in a function like this. All right, our next function, y equals x, let me zoom in a little bit. It would just be your standard line, like y equals x, so your y-intercept is 0, and your slope would be 1. So you would go up 1, right 1, down 1, left 1 if you want to go the opposite direction. But our, sorry, that's not connected, but it's close enough. But that's our y equals x function. So that's our starting points before we would do any rules. So the domain for a line would also be all real numbers because it goes to the left and right forever. Or you could do negative infinity to positive infinity. But I'm just trying to show you that new symbol. Our range would also be all real numbers because it goes up and down forever as well. Like there's no gaps. So a lot of these functions we'll see will have at least for one of them, either the domain or range, all real numbers. So like I said, when we did domain of like what we saw in our last quiz, like a lot of those domain and range questions were a lot harder than a lot of the functions we'll look at, because a lot of the functions we'll look at this year, it'll just always be all real numbers for their domain and range. So there's not as much thinking to do. If you're not familiar with an y equals x squared, you can always just make a table of values. So for example, if you just plug in these 5 points, like -2 squared would be +4, just because -2 times -2. If you put it in a calculator, do make sure you put parentheses around it. If you just type in -2 squared, it's going to give you -4, the wrong answer. So you got to put parentheses around a negative number when you square it, or just remember any number squared will always be positive. -1 squared would be 1, 0 squared would be 0, 1 squared would be 1, 2 squared would be 4. You might notice some symmetry between our table. That's one thing when we do more with quadratics we'll talk a lot about. But if you plot it, I'm just going to zoom in. You have a point at 0, 0, 1, 1, -1, 1, 2, 4, and -2, 4. So it looks roughly like that, and you try and make it kind of round. It's not like a sharp point. We'll see an absolute value makes more of a V. The x squared makes more of a U shape. But our domain would be all real numbers, because it's going to keep going to the right and it's going to keep going to the left. Even if it's growing slow those directions, it'll always keep going to the left and right. So any x squared function is going to have a domain of all real numbers. Our range of our parent function would be from 0 to infinity. But just so you know, when you do some transformations, your range can change. But the domain will never change. But that's just of our parent function. So these are probably pretty familiar. You should have at least done some stuff with quadratics in Algebra 1. I don't know how much it's emphasized, but I know that's part of the error test, so I know they throw that in. That used to just be an Algebra 2 concept, but a lot of things get kind of pushed in Algebra 1 because of those error tests. But these are kind of the ones, some of the most common ones. But looking at x cubed, if you've never graphed a cubic function, you probably haven't, I would guess. Crap, and I might have to write, I'll try and squeeze this in. But you would have, like, if you plug in your kind of your standard x values, like -2 to the 3rd power, if you plug that in, you're going to get -8. Like you could plug these into a calculator if you don't believe me. -1 to the 3rd power would be -1, or really it's -1 times -1 times -1. Basically the same number multiplied by itself 3 times. 0 times 0 times 0 times 0. I think I said 1 too many zeros. 1 times 1 times 1 would be 1. 2 times 2 times 2 would be 8. So if you graph this, like you have a point at 0, 0. You have a point at 1, 1. You have a point at -1, -1. And then you have a point at 2, 8. Hopefully I counted right. 1, 2, 3, 4, 5, 6, 7, 8. Then -2, -8. But it kind of like makes this, like how it's kind of a weird shape. I always kind of describe it as kind of like a bent paper clip. Like you kind of bent around a paper clip. But it looks like this. And I'm sorry, I'm kind of squeezing it in, but so our domain for a cubic function, even though it almost looks like it's going vertical, it's slightly going to the right forever, and it's slightly going to the left forever. So our domain would once again be all real numbers. And our range is the same idea. It goes up and down forever, so it would also be all real number, or it goes from -infinity to positive infinity. So this symbol just is a nice kind of save some time instead of writing out that interval notation. Our next function is an absolute value, and I'm sorry, I'm kind of writing it below, but here's the table of values for an absolute value. Remember, an absolute value, if you plug in a negative number, it just turns positive. And positive numbers stay positive. So this would be 2, 1, 0, 1, and 2. So you can see. But basically, because remember, an absolute value tells you how far away from 0 you are. So if you're -2 on a number line, you're really +2 away. So if you graph it, though, an absolute value makes a V shape. Oh, crap. It should be 2, 2. So I'm just plotting those points 0, 0, 1, 1, -1, 1, 2, 2, and then -2, 2. And then you just connect it with a sharp V. It's basically like 2 lines, kind of just in the positive parts. So our domain and range of a piecewise function, sorry, I know this is kind of all over the place. Oh, what am I writing the answer? But our domain would be all real numbers because it goes to the left and right forever. Our range would just be from 0, because the lowest it goes is 0, and it goes to positive infinity. Our last function, the square root of x, we're actually going to use some different values of x for this one, because you can't take the square root of a negative number. Like if you type the square root of -1 in your calculator, it's going to give you domain error or say an error, depending on what calculator you have, or undefined. Like different calculators come up with different error messages, but you're going to get an error. So you can only plug in 0, and you can only plug in positive numbers, but I'm going to pick numbers that work out nicely. So I'm picking perfect squares. Numbers, when you take a square root, you get a whole number. So for example, the square root of 0 would just be 0. The square root of 1 would be 1. The square root of 4 would be 2. And that's probably plenty. I mean, you could plug in 9 as the next perfect square, but that should be plenty of points. So if we plot this one, you start at 0, 0, 1, 1, and then 4, 2. And just a heads up, I don't expect you to memorize these graphs, like these standard points. You will kind of learn them when we do a lot with specific types of functions. You'll just, because you plot them so much, you kind of just memorize them, or you learn them through time. But if you ever forget like how to plot the original function, you can always just make an XY table. So it shouldn't be something you have to memorize, or like it's not like something you have to cram. I probably won't ask you like just to graph a parent function. I just want you to, like, the goal from this is if you have an absolute value function, I want in your brain to be able to kind of visualize, oh yeah, that's that V-shaped graph. So you kind of know what it looks like before you actually start graphing something. Or if it's an x cubed function, I want you to be able to see in your head, oh, that's that bent looking paperclip one. So you can kind of visualize it before you actually start the graphing process. That's kind of the goal from this section, other than just the transformations. But our domain for the square root function would be from 0 to infinity. And our range would also start at 0 and go to positive infinity, because that's as low as it goes, and it goes up forever, ever so slightly. But these are our parent functions. And I know I threw a bunch of stuff like kind of crammed in here. I'm not going to worry about these definitions. I assume you guys already know those from what we've talked about before. So we won't define those again. But these are kind of like some of the most common functions we've seen. Like, for example, section 2, or chapter 2, we've been looking at a lot of linear functions. So like y equals x. Chapter 4, we're going to see in the textbook, is looking at a lot of quadratics or x squared functions. And then I think it's chapter 6, we look at a lot of root functions. It might be chapter 7, but just so you know, like these different types of functions will be kind of big topics in this course. We'll do a lot with them. But right now I'm just trying to expose you to them. So if when we do graph, or you do have to graph one of these, at least in your head, you can kind of see them. But I'm gonna, all right, so the first section, they're gonna just give you a function. So it says the graph of y equals f of x is the solid black graph. So it's not one of the parent functions we just talked about, but this is our original. They wanna know which function represents the dotted graph. So if you kind of notice, to go from the black to the red, it looks like it moved to the right. That's all it did. And maybe actually looks like it went down a little bit as well. So these are going to be multiple choice. We're going to look for a rule that would move it to the right and move it down. So if you have your rule sheet, like if you want to look at those rules, like the f of x plus or minus k, the f of x plus or minus h. So like one thing you can do is you can just find like one point on your graph. So like, for example, I have this point, it looks like at -2, -5. If I can figure out how did it move to the same point on this graph. So for example, this point at -2, -5 looks like it moved to +2, -6. Or in other words, if I just kind of look at what it did, it went right 1, 2, 3, 4, and it went down 1. So I want to figure out which one of these equations means go to the right 4 and go down 1. So if you look at your rule sheet, you should see, and here I can annotate, I can type what I'm kind of saying, but if you look at your rule sheet, remember, a plus or minus h or a minus h in parentheses is what moves it to the left or right. So remember to go right, it's kind of opposite. So that would be -4. That means go right 4. If you have a minus on the inside, that means go right. And then to go down 1, you put a minus on the outside of your parentheses. So looking at these choices, it would be the third choice. Oh, crap, I'm still making text box. I got to click out of this. Okay, so that's our first example. I'll pause the next section. So your other section in deltamath is they're going to give you one of the parent functions, and they're going to graph it for you. So like right now, what's on your screen, like what they start with, like right now we just have like the graph currently, like those points right now is, I can't do the square root symbol, so I'll just put square root. But right now we just have the square root of x. Like this is the original parent function that we saw in our notes earlier. So they're giving us some transformations to do. So they added this -2 in front of our parent function, or our original function. So we're going to do those rules to our function to get the new answer. And one nice thing, at least that at least from what I've tried in this delta, is if you move one of the points in what you're supposed to do, all the points will move with it. So you don't have to move every one of these points over and over by themselves. I think you might have to move the green dot and the green dot individually. Like for example, if this function, let me just kind of show you, but if this function, crap, damn it, I mean language. But like for example, I think if it moves up or down, well, actually, yeah, if you got to move it like up or down, like you got to move the green dot, like if it moves like the whole function left or right or up or down. But if it has like a reflection, you got to move it like this, or if it had a stretch or compress, like it shrank or it grew. All right, but I'm going to put it back like it was. But that's just kind of how this works. So this -2, well, first thing I would notice, it's a negative. That's a reflection. Like if you have a negative in the very front and over the x-axis, because that's the only type of reflection you should see. Like you shouldn't actually have to reflect it. We'll see, but I'm pretty sure they don't ask like that. But if they do, if the negative was like inside your square root, like in front of the x inside here, that would be a horizontal, like a y-axis reflection. But so the first thing I'm going to do is reflect. So I'm just going to move this point here. It's at +2 in terms of my y value. So it would flip to -2, like over the x-axis. And then this 2 is a vertical stretch. Like if you look at our rules, that's like the a, if a is greater than 1. So it's going to stretch. Basically, it's going to double the y value. So if our y value is -2, it's going to double to -4. So, and from what I've seen, it seems pretty forgiving. Like as long as you're, because it's hard, you can't really get your point exactly, but as long as you're in the general area, it seems like so it must have some kind of like general forgiveness it gives. Because so far I haven't had any issues. Like my cursor's not exactly where it should be. So as long as you're pretty close to the points, it seems like it'll give it to you. So I haven't noticed anything because I was kind of worried about that. Let's look at another example. So this time we have our x squared parent function. That's our y equals x squared right now. And they're applying these rules. So just so we're clear, right now our graph is this. Y equals x squared. So we've got a couple rules to do. The first one, oops, crap, let me keep, the one thing that's when you write on the screen, you got to make sure you close it before you move on. Okay. So the first thing you have is this negative. So that's a reflection. So you can just pick any of your blue points and reflect it. So this point was up 1, so it's going to reflect over the x-axis to -1. And all your other points you can see move with it. So like all these other points reflected as well. It doesn't matter which blue point you pick. And then this -1, since it's not like inside parentheses, it's outside your variable, it means you go down 1. So you got to click the green dot to move your function up or down or left or right. So if you pick the green dot, move it down 1, that should be our answer. Just one thing I want to say, because sometimes this -1, people might be confused. Well, how do you know it's up or down or left or right? So let me just type something really quick so you can kind of see. So if it, let's say you thought this meant go right 1, because it's a -1, maybe you thought it meant go right 1 because it's opposite for left and right. What it would look like if it meant to go left 1, it would have parentheses like that, or right 1, it would look like this. This is what it would look like if they wanted you to move left or right. They would put parentheses around your function. For some functions like the absolute value, it'll be like, it won't have parentheses, it'll be like inside your absolute value bars. Or if it's a square root, it would be underneath the square root with your x. So it's not always going to be inside parentheses, but like depending on the type of function. But so if it's like an absolute value, these parentheses would be absolute value bars. But that's the key difference between going left or right. If it doesn't have like parentheses or some kind of part in your function, if it just looks like this is considered like on the outside of it. So if it's going to be a horizontal change, they're going to add those parentheses. Like that would mean go left too. Okay, so maybe that'll, because that's probably going to be a common maybe misconception I could see. So that